Well, today I'd like to visit with you about about F equals ma in the R-Theta-Z coordinate system. And just remember, in the NTB coordinate system, which we just got done with, the path is defined or restrained. Often it's defined by an equation, but it's definitely the particle is restrained to move such so that it stays on the path. All of the motion, all of the velocity is tangent to the path. There's never a normal component of velocity, and we discovered there was not a B component, vertical to that plane component of velocity. Obviously it can have acceleration normal, can have acceleration tangential, but no acceleration in the B direction. In the R-Theta-Z coordinate system, the path is not restrained or defined in the same way. It can have acceleration in both acceleration and velocity in all three directions, in the R and the theta and the Z. Now, if we can have acceleration in all three directions, then we need to have an acceleration equation, or an equation of motion for all three directions, or all three coordinates. So here are our three equations. Some of the forces in the radial is equal to mass times acceleration radial. Some of the forces in the theta, some of the forces in the Z are similar. We'll find that it's best to use the R-theta approach when the path or position is defined in R-theta, and we'll talk a little bit more about that. Okay, back just from chapter 12 a little bit. If we have a path that is in three-dimensional space, we have an R and a theta and a Z perpendicular to that path. Just like before, we'll need to evaluate R, R dot, R double dot, theta, theta dot, and theta double dot, and then we'll plug them into the equations for acceleration in the theta direction and acceleration in the R direction. And if you recall those equations, and then the velocity equations, the velocity R is R dot, velocity theta is R theta dot. Okay? Now in the Z direction, I believe we did this before, but the acceleration in the Z direction is Z double dot, and that A is equal to dv dt and AdS equals VdV apply in the Z direction. Okay, we're going to talk about a variety of types of problems, and we're only going to solve a couple of them, but just recognize that R-theta can be in a variety of configurations. It could be in the horizontal plane. So this is a car on a track. We did one of these in class where we had an R-theta. It could be in the vertical plane, something like this, where this thing is rotating and shoving up that little ball. It can be forced by a bar, or it can be not forced. In other words, the particle can be moving on its own. I guess not forced by a bar. It's going to be moving, but for some reason, maybe there's a force on it. Maybe it's just got some velocity. It can have a defined path like this, or it can have a not defined path like a robot. It can be two-dimensional and just flat, or it can be a three-dimensional problem. So, and in class, we're going to do a little more of this, but circular motion problems like this. In fact, I think you did one or two of these for homework. But circular motion problems like this can be solved in either NTB or R-Theta-Z, and we'll talk a little bit about that as we go forward. All right, what I want to visit with you about is the two general cases of problems we're going to talk about in this video anyway, is that unconstrained path. And a robot is a good visual, I guess, of an unconstrained path. But this is a vertical configuration. The path is not defined. There will be some R and there will be some theta that is given to you, or you'll have to figure out. But what we'll have to do is draw our axes in the R direction and the axes in the theta direction, just like we did before. What we'll recognize is there are forces on here such that there will probably be a gravity force that will be coming down, and there will be a force pushing this thing in the R direction and a force pushing this thing in the theta direction. Okay? But those are the basic components that we'll find in an unconstrained path: a pushing force and a gravity. Now, if it's constrained to move on a fixed path, for example, this bar here pushing this thing up, we may also find we'll find components of force that are supplied by the bar itself. In other words, the bar is pushing on this particle, but we'll also find components of force that are supplied by the path. And so we'll have more components of force that we'll have to deal with. But just recognize here, as this thing moves up here, there will be a force pushing the bar in this direction caused by that bar right here. Oops, sorry, the bar right here. And if this is the R direction pointing out like that, this will be, if theta is going this direction, this will be the theta direction going up like that. So this would probably be considered P theta. In other words, what is being pushed on, or what is pushing the particle on, pushing the particle by the bar itself. But recognize also the path has some forces on that little particle too. And if you'll notice that this particular path is a vertical path, it's going up like that, but there's going to be a normal force. And the normal force is always going to be perpendicular to the path. Perpendicular to the path. And there may be some friction. If it's moving up like this, you may consider that there may be some forces tangential to the path. In this case, it might be a frictional force. And there may also be an mg. An mg may be, will have components in both the r and the theta direction. In fact, all of these things will have components in both the r and theta direction. Our challenge then is to recognize all those components, or recognize the forces first, and then break those forces up into their components of r and theta, and then solve for the unknowns. So then, let me give you the actual steps. First of all, we'll draw the axes. Draw those coordinate axes. You draw the free body diagram and make sure that you get all of the forces on the free body diagram. You define all the pieces, r dot, r double dot, theta, theta dot, and theta double dot, and then you sum the forces in the r direction equals mass times acceleration in the r, and sum of the forces in the theta direction is mass times acceleration in the theta direction. And solve for those unknowns. And you follow this process exactly, you'll be in good shape. Well, here is a very typical R-Theta system. It's a little robot that's gripping a little item here, and it's extremely common in industry. So what we're asked to do here in this problem is try to analyze the forces involved. And so recognize that it's an R-Theta system by the fact that the dimensions or the positions of the particle are described in terms of its r, distance away from an origin, and an angle theta. That's what lends us to understand that it's an R-Theta type of problem. So first of all, let's define our axes. And if you recall, we got the r-axis, which points straight out from the radius, or excuse me, from the center. The theta axis goes perpendicular to that, and so this will be the theta axis. It'll be positive in the direction of positive theta, and theta is defined as positive that way. So r-axis. Now we need to make sure we draw a free body diagram. And this is in the vertical direction, vertical orientation, which means that gravity counts. And so I'm going to draw an mg coming straight down there. And we're tasked to try to find the forces to manipulate this thing in the r direction and the theta direction. So I'm going to put a PR, we'll call it PR going this direction, and a P theta going in this direction. Okay, those are the main forces on our free body diagram, but let's also draw the components of mg, because what we're going to have to do is try to look at the forces in both the r direction and the theta direction. So I'm going to draw my component here of mg in that direction, and another component of mg in this direction. If we look at the geometry, we can see that this is the same angle as that, so that makes this the mg cosine, and this will be mg sine. Okay, let's look at the description of the problem carefully. We start with an angle, or with a position of 0.75. This is the piece that's changing. It says that in the beginning of the problem, or at the instant shown, is when theta is equal to 30 degrees. We have a theta dot is equal to 40 degrees per second, and a theta double dot is 120 degrees per second. At the instant shown, we have this fixed position, and then L is 0.5, L dot is 0.4 meters per second, and L double dot, it's kind of hard to see there, but that is equal to negative 0.3 meters per second. Well, we need to get this in terms of radians. Now the angle we can leave in 30 degrees if we want, or we can say that that is equal to pi over 6. 40 degrees per second is 0.6981 radians per second, and theta double dot is equal to 120 degrees per second is 2.0944 radians per second squared. L is this distance, but we need to have this in terms of r, and r is the position from the end. So I'm going to say that r is equal to this 0.75 plus the 0.5, so that'd be 1.25 meters. R dot is going to be the same as the L dot, so that is 0.4 meters per second, and R double dot is equal to negative 0.3 meters per second squared. In other words, the change in the total length is defined by this L dot, and so those are the same for R dot and L dot. Okay, remember in chapter 12 we had to find the acceleration in the R direction and the acceleration in the theta direction. So I'm just going to plug all these numbers into this equation, and I'll let you fill in the gaps and do the math, but that turns out the acceleration in the r direction is minus 0.90918. That would be in meters per second squared. The same with acceleration in the theta direction. If I plug all those numbers into that equation, from chapter 12, we should be familiar with that, 3.17648. And I'm using a lot of decimal points here just because I don't know if it's going to be necessary or not to improve the accuracy. Sometimes 3 decimal points or 3 significant digits is enough. Sometimes you need a little bit more. All right, how do we analyze the forces? If we look carefully at the force, at the free body diagram, we see we have several forces in the r, or we have 2 forces in the r direction, and we have 2 forces in the theta direction. So all I have to do to find those forces is just sum the forces in the r direction. So let's put that up here. Forces in the r direction. I got PR, and that's going to be in the positive r direction. Looks like my component of mg is going in the negative direction, so I'll say plus PR minus mg sine theta is equal to mass times acceleration in the r direction. I'm trying to solve for that force in this force here, the applied force in the r direction, so I'll just say PR is equal to my mass. Factor that out of there, that's equal to 1.2 kilograms. I guess I didn't mention that at the beginning of the problem, but it's 1.2 kilograms times the acceleration in the r direction, which would be minus 0.90918, plus, bringing that onto the other side of the equation, mg be 1.2 over, 1.2 times 9.81 times the sine of 30 degrees, and we get the P in the r direction of 4.795 newtons. That's P in the r direction. All right, so that's the first piece of the puzzle. Forces in the theta direction. We do the same thing. Sum of the forces in the theta direction is mass times acceleration in the theta direction. So let's look back carefully at the free body diagram. In the theta direction, we have a P in the theta direction. We have a component of mg in the negative direction. So I'll say that P theta minus mg cosine theta is equal to ma theta. And I can bring that together over here. P theta is equal to 1.2. A theta from before is 3.176 plus mg 1.29.81, and I got the cosine of 30, and that's equal to 14.00 newtons. That's equal to P theta. All right, so that's the conclusion of that. That's all we need to do. Find the components of the 2 forces, or find those 2 forces. If we want to find the total force, we could take the square root of the sum of the squares and draw it up like that. That wasn't asked for in this problem, so you don't need to solve for that. Well, here's another R-theta problem. This may not be quite as typical in the exact configuration as a robot, but the analysis of this and the way you go about it is extremely typical in all types of problems where the path is constrained. In this case, it's constrained to move, or this little ball here is going to be constrained to move along this path. So the path is defined, and there will be some forces caused by the path, as I mentioned earlier. Okay, so what's going on? This arm here is rotating like this. This little ball is sitting here in the little crook between the arm and the actual hemispherical surface, and as long as I don't push too hard, the ball will stay there, but we're trying to analyze the forces that are on that little ball as it sits. This is in the vertical plane. Gravity is coming down, of course. So we'll first start by drawing our axes in our free body diagram. Alright, so our axis goes straight out from the center, so I'm going to call that the R axis. Theta axis comes straight out there from there. It is in the vertical plane, so I'm going to draw the mg coming straight down. Okay. Now, we'll be trying to analyze the forces on this ball in both the r and the theta direction. So I'm going to draw, you know that there's going to be a pushing force. The bar's rotating in this direction. You can see the little omega kind of, or the little angular sign here that says it's rotating in that direction. There will be a force straight in the theta direction pushing on the ball. I could draw the force right there, but I'm going to draw it up here for convenience because that way the drawing doesn't get quite so crowded down below. But recognize that this is p theta, but it's being caused by the force of the bar pushing on the ball in that direction. Now in the r direction, there really aren't any forces in the r direction caused by this bar. The bar only pushes in that direction. It's only pushing tangent right on that surface right there, so there really aren't any forces in this on the ball in the r direction caused by this rotating bar. I'm going to put a PR in the drawing, but recognize when we solve the problem that that actual pushing force will be equal to 0. There'll still be forces in the r direction, which we'll have to analyze. Okay, next thing is that there is a force caused by the actual surface. The surface is pushing on the ball. It's keeping it from, I guess, rolling down this way. So recognize that the normal force caused by the surface is pushing straight on the ball perpendicular to the tangent, or perpendicular to the surface. So I'm going to draw that right there. That is going to be my normal force, pushing up like that. Alright, that's normal force. Now let's draw the components of the forces in all of the directions. There's going to be a component of the normal force in this direction. This is, well, let's go back and talk about the angles. Recognize that this particular piece, this particular problem is it looks like this is a triangle here that's going to be changing in shape as this bar rotates around. But this is an isosceles triangle. This is the radius of this little circle, so that is RC. This turns out to be also the radius of the circle, and so that because those two legs are going to be the same for all values of theta, that makes that angle theta as well. So this is an isosceles triangle with those two legs equal. That makes those two angles equal. If you do the geometry, you can see also that as this perpendicular line there coming from the radial direction, this angle will also be theta. Okay, now let's go back to drawing the components of the forces. This is the normal force component in the r direction, and it looks like that's going to be the cosine of theta, so this will be normal cosine of theta. It will also have a sine component, and it's going to get a little busy down here, so I'm going to put the sine component of theta up in that direction. So anyway, it goes right there, but this will be normal sine theta. Alright, how about mg? mg is going to have components in the r and the theta direction, so I'm going to put the mg in the theta direction down there, so that is mg cosine theta. And it will also have an r direction, and boy, it's going to be hard to kind of draw it in there, but I'm going to draw it right like that. As we're looking at it, you might be able to discern that later, I don't know. But anyway, that component right there is going to be the sine component, so that is going to be mg sine theta. Okay. Now that I've got all the forces now and got our free body diagram, again, it looks a little busy, but I hope that you were able to follow that. Let's look at the description of the drawing, or description of the problem, and try to figure out what's going on. It says that the ball weighs a half a pound, 0.5 pounds. It's guided by on the circular vertical path it says this distance r here, this total distance is 2r cosine of theta. We've got a definition for, or an angular velocity of theta dot is 0.4 and an angular acceleration of theta double dot of 0.8. And it's looking for, at the instant theta equals 30 degrees, we're looking for those forces. Okay, and it also says the radius of the circle is 0.4. All right, so let's write all those things down. Theta dot is equal to 0.4. Theta double dot is equal to 0.8. And this is in radians per second. Radians per second squared. R is given as a function of theta, so we're going to have to do a little chain rule derivative here. So I'm going to say R is equal to 2RC cosine of theta. That's given right there. R dot, we're going to have to do the chain rule. So 2RC is a constant, so 2RC. And the derivative of the cosine is the minus sign. And I need to put a theta dot on there from our rules before. So this is dr d theta dt. Now to do r double dot, I need to do the product rule. So again, 2rc is a constant, and I'm going to say that is my u and that is my v. So I'm going to say u times the derivative of v, so that would be minus sine theta double dot plus v times the derivative of u. Theta dot, derivative of the minus sign is the minus cosine, but that minus cosine is the derivative of sine with respect to theta, and I also need d theta d theta, then d theta dt. So I need another theta dot. And I know many of you have got that figured out by now, but I'm going to simplify that and say that this is 2rc minus sine theta double dot minus cosine theta dot squared. All right, so those are my values, or my derivatives anyway. Now what I can do now is plug at theta is equal to 30 degrees. I guess I didn't write that down, which is equal to pi over, what is that, pi over 6, I guess. Okay. Now if I plug all those values into here, I also need r is equal to 0.4. R is equal to, well, it's given there, r is equal to 0.4, and I guess I could solve that for all those things, but I can plug, I can use that value straight out. So let's just say that r is equal to 0.4, r dot, plugging, RC is equal to 0.4. That's what we're looking for. And then R is going to be equal to, because it's not going to be 0.4. R is equal to, what did I calculate that as? 2 times 0.4 times cosine of theta. R is equal to 0.6928. And R dot is equal to negative 0.16. R double dot is equal to negative 0.4308. That would be meters per second squared, meters per second, and in meters. Okay. Now, done all the hard part really. The free body diagram sometimes is tricky. Sometimes taking these derivatives is tricky. Finding the forces and using the force equation is usually very straightforward and just plug and chug. So the ball weighs, the mass is 0.5, or the weight is 0.5 pounds. So I'm going to sum the forces in the R is equal to mass times acceleration in the R. And what do I have in the R direction? I've got a PR. So I'll put that PR. And I'll look carefully at the drawing. I've got an N cosine theta plus N cosine of theta. I know you can't see me writing here, but I'm going to do it down here and then move it up. N cosine theta, and then I've got an mg sine theta. What we did before is going in the negative direction. Minus mg sine theta. And that's going to be equal to my mass times acceleration in the r direction. Now I'll put it up here for you. Mass times acceleration in the r direction. All right. Previously we said that that is going to be 0 because there was nothing in there. And I can now solve this for normal force. Let's go ahead and complete this. The mass times acceleration in the r direction, if you recall, the AR is r double dot minus R theta dot squared. And if I can actually solve this for normal force, I know everything here. I know mg is 0.5. The mass is obviously 0.5 over 32.2. And I think what I'll do is I'll write the whole equation out here for you, and then you can follow my math in a little bit later. N cosine of 30 minus 0.5 sine of 30 is equal to 0.5 over 32.2. Our double dot is minus 0.4308 minus r is 0.6928. Theta dot squared is 0.4 squared, and n turns out to be equal to 0.2789. 89, and that's in pounds because we're in the English system. All right, that doesn't quite get me the answer I'm looking for, but that does help me get there. I need to find that normal force right there before I can move on to the theta direction. So now let's move to the theta direction. Sum of the forces in the theta direction is equal to mass times acceleration in the theta direction. And let's look carefully at the drawing. What forces do I have in the theta direction? I have this pushing force. This is the actual force that we're looking for. P theta is the pushing force from the bar onto the little ball. I have a normal component in the positive direction. I got that n sine theta, and then I have an mg cosine theta going down in the negative direction. So let me put all those things in there. I got P theta plus n sine theta minus mg cosine theta is equal to ma theta, which we recognize as m r theta double dot plus 2r dot theta dot. All right, I'll spare you the math here. You can solve every single one of these terms now. You know normal, you know sine, you know mg, you know m, and you can follow me on, you can look at the details when we post this online. But P theta is equal to 0.300 pounds, and that's the actual force that we were looking for, the actual answer to the problem that we were looking for, 0.3 pounds.